Have you ever wondered how electric motors turn or how speakers produce sound? It all starts with a fundamental interaction between electricity and magnetism. When an electric current flows through a wire placed inside a magnetic field, a physical force is generated. This phenomenon, known as the Lorentz force, is the bridge between electrical energy and mechanical motion. By understanding how current, magnetic fields, and force vectors interact, we can harness this power to drive modern technology. The magnitude of the magnetic force depends on four factors: the amount of current, the length of the wire inside the field, the strength of the magnetic field, and the angle at which the wire cuts through those field lines. Current, represented by I, is measured in amperes. L is the length of the wire in meters, and B is the magnetic field strength measured in teslas. When these values increase, the resulting force on the wire also increases proportionally. The angle theta is crucial. The force is at its maximum when the wire is perpendicular to the magnetic field. However, if the wire runs parallel to the field lines, no force is generated at all, regardless of how much current is flowing. This rule reminds us that the force is always perpendicular to both the current and the magnetic field. It creates a three-dimensional relationship that is fundamental to electromagnetic theory and engineering applications. The result is 1.5 newtons of force. While this might seem small, in the world of microelectronics or high-torque motors, these forces are precisely calculated to ensure smooth and efficient operation. By reducing the angle, the force drops to 0.75 newtons. This demonstrates why engineers align components in motors to ensure the current and magnetic field stay as close to perpendicular as possible for maximum efficiency. Let's practice the right-hand rule. If the current is flowing into the screen and the magnetic field points to the right, where is the force? Point your thumb into the screen and fingers to the right. Your palm should be facing downward. Therefore, the magnetic force will push the wire toward the bottom of the screen. This directional control is how we make speakers vibrate back and forth to create sound waves. In an electric motor, we use a loop of wire. The force pushes one side of the loop up and the other side down. This creates a torque that causes the motor to spin, converting electrical energy into mechanical work. To summarize, the magnetic force on a wire is determined by the current, length, field strength, and the sign of the angle. We use the right-hand rule to find the direction, and this principle powers everything from motors to maglev trains. Here is a quick question for you. If you double the current flowing through the wire but simultaneously cut the magnetic field strength in half, what happens to the total force acting on the wire? Think about the formula. Since the force is proportional to both current and field strength, doubling one and halving the other cancels out, leaving the force unchanged. Thank you for exploring electromagnetism with us today. Generated by Vision Solve AI.